Amy is a senior data scientist on the advanced analytics team at Opendoor. Her responsibilities include defining and leading pragmatic casual learning practice at a company level using advanced experimentation, inference, and decision science techniques. So welcome, Amy.
Hi, everybody. First, thank you, Annie, for the great showcase of all the cool design work your team have been working on. I'm a senior data scientist at Opendoor. I'm going to give you a flavor of the type of problem and the project data scientists are working with at Opendoor. Specifically, this is a multiple hypothesis testing problem. As you all know, this multiple hypothesis testing problem means when we do more statistical tests, we are more likely to make a type 1 error, which is a false positive discovery. Here is an illustration when we test 20 times on different colors of jelly bean and how they show a correlation with acne. 1 out of the 20 tests will show a significant correlation, even though it's purely out of random noise. So that's telling us whenever we do statistical tests, we want to control the overall type 1 error rate in case there is an inflation, cumulative inflation by the more tests we do, the more likely we are going to see a significant result. At Opendoor, the problem came up frequently, specifically for product improvement. Sometimes we want to track multiple outcomes of interest, not just one. So when we do want to evaluate the effect of certain product change on long-term or short-term outcomes, we are encountering this problem. Or if we want to dissect the data set into multiple subgroups and do a statistical test within each subgroup, we are encountering the same problem. And sometimes we want to run an experiment with multiple treatment groups, not just one case versus one control group. When we have multiple treatments, we want to test each one compared to the other one, which one give us the best lift. So all the scenario will generate this multiple hypothesis testing problem. If you look up the literature, you will find out statistically there are ways to control this type of type 1 error rate inflation by adjusting your p-value. For example, some common method you will see are Bufferini correction or Holmes method, false discovery rate control. Those are all thoroughly researched statistical methodology to control this problem. However, practically, we have some objections when using this type of statistical method. People will say, p-value adjustment are actually pretty arbitrary by number of tests we are going to consider. How do you decide what's the correct number of tests we are going to adjust? Should we adjust tests we have done in the past? Should we adjust tests have been done in other teams, but not specifically our teams? So this number become very arbitrary, and sometimes people will use this arbitrary concept to falsely adjust the total number of tests. The other objection is when we reduce the type 1 error, we are inherently increasing our type 2 error rate, which means we don't have enough power to detect a significant true result, which also means we are going to increase our total sample size. So to solve this controversial problem, as a data scientist, we come up with very practical recommendations and strategies, not only for researchers and data scientists, but also for readers and stakeholders who are going to review and read those reports. For example, we would recommend not just focus on interpreting the p-value part, but also focus on the true magnitude or the effect size of the finding from the data. Also, we want to pay attention to the quality of the study and the data set. So focus on more from the design and the data quality side of the report and the study, not just purely based on the p-value from the study. For researcher and the data scientists, we come up a set of statistical methodology recommendations. For example, when handling correlated outcome or metrics, we have this index method that can utilize the correlated information from multiple outcomes, try to aggregate the common information and reduce the type 1 error rate. Or we have this Bayesian multi-level modeling method. So completely move away from the frequentist p-value based decision-making process and move to a more Bayesian probabilistic recommendation system. Practically, we also give recommendation. One of my favorite recommendation is divide the error rate into a family-wise error rate control system based on theoretical related test groups. Let's say you have two set of tests, 3 tests all measuring user satisfaction. You may have different metrics, but you are going to run 3 tests. They are all follow the user satisfaction category. You have another set of tests which are testing the total error rate or page load speed, which can fall into this safety metrics category. In this case, instead of splitting the total error rate across all the tests equally, you can divide them by the 2 families. So each family can share their own overall error rate. Now that's just one project data scientists are working on at Opendoor. I also want to use this opportunity to introduce some of the other projects data scientists work with at Opendoor. So why is Opendoor investing so much on data quality and the data rigorous and the data science role? It's because Opendoor business is really unique and it's very complex. If you think about housing transaction, it's very important, and maybe you only do 1 or 2 housing transactions in your whole life. So it's very complex, the transaction process. Second challenge is our data is super sparse due to it's a rare event. We don't have repetitive interaction with the customer. Sometimes we only serve the customer 1 or twice in their whole lifetime. So it brings a lot of analytical and the statistical challenge. We don't have the luxury of the e-commerce or internet type of traffic. So a lot of the decision we are making need to depend on statistical inference and the statistical expertise at Opendoor. The last point is optimization. We want to produce the best user customer experience with a constrained amount of time and a constrained cost. So we want to work within limited costs and trying to optimize within the constraint and produce the best customer experience. I'm going to share with you some other typical projects our data scientist team work with. For example, in the buyer team, we study the local housing demand and the price elasticity, and we feed that information to our resale pricing team in order to better or more accurately price the resale price for the home we acquired. In the seller team, we try to target specific seller group and provide more customized seller experience by serving based on seller input, their characteristic, provide a different type of unique service. So that's all optimization model our data scientist team work on. From pricing side, we want to understand how to combat risk, adverse selection, and the competition, and build all the factor and the macro information into our pricing model. So that's an overall introduction for the data science team and some of the cool projects we are working on.